this equation is the expression for a conductor which is moving in a uniform magnetic field with certain velocity v and covering a distance of dx. So due to the drastical change in magnetic flux, there is an induced current in the bulk pieces of a conductor. Whenever there is a production of current in the primary coil, there is a existence of magnetic field in the secondary coil, and this magnetic field in the secondary coil increases the induced current in the secondary coil, through which the EMF is also increased. Hello everyone, I am Vrinda, Faculty of Physics from Vidhyaashram Pre-University College, Mysuru, welcoming you all to session 2 of chapter 6, and chapter name is Electromagnetic Induction. In today's class, we are going to study the self-induction, mutual induction as well as generator concepts. So here first of all, we study about Lenz law and the conservation of Lenz law. We had already studied what is meant by a Lenz law. Lenz law means whenever there is an induced EMF, that induced EMF with different polarities. Remember, the different polarities, the polarity is said to be different for the EMF in case of the Lenz law, okay? So, EMF induced having different polarities, it induces a current in the coil. The induced current induces a magnetic field in the coil, and this field opposes the flux which is upcoming from the loop. So this is how exactly the Lenz law goes on. That is, whenever there is a magnetic field which is created due to the induced EMF, it opposes the actual flux which is passing through the loop. Opposition is given there, and that is actually studied in case of a coil. Whenever there is a coil, you consider there is a coil, and suppose you hold this coil with the help of your right hand by using the right hand thumb rule, okay? Just hold this coil in this way, such a way that the thumb indicates the direction of the flow of current and the curled finger indicates the direction of the magnetic field, correct? Because the current as well as magnetic field is perpendicular to each other. So when there is direction of the current in this manner as well as the flow of the magnetic field, it is said to be anti-clockwise direction. The flow of current is said to be anti-clockwise direction, and here this happens when the pole, that is the bar magnet's pole, north pole, is moving towards the coil. It is moving towards the coil, okay? So that is, whenever we hold a bar magnet near to the coil and we move that bar magnet towards the coil, what happens? The flow of current is said to be in anti-clockwise direction, and this anti-clockwise direction possesses certain magnetic dipole moment in a loop, and that magnetic dipole moment in a loop is said to be north polarity. So it is like, it is said to have north polarity. What? The dipole moment of this coil. So, however, we can give this as in case of anti-clockwise direction, and it is said to be north. It is in terms of N, that is anti-clockwise direction. Okay, this is an anti-clockwise. This arrow indicates that it is an anti-clockwise direction. Similarly, now whenever you take the coil back again and when you move the north pole of the bar magnet away from the coil, again what happens to this coil? That is, you're holding in your right hand downwards, so the current is indicated in the direction of clockwise direction, okay? This is the indication of current, and when you hold downwards, you have the magnetic field in the other direction. But the magnetic field as well as current both are perpendicular to each other. So here you can give this symbol as south pole, that is the polarity of the magnetic dipole moment. He is having south polarity. This is having north polarity and this is having south polarity. The induced EMFs are having polarities, and that is studied under Lenz law. This is the main thing what you have to understand. Induced EMF having polarities in which law? It is Lenz law. Lenz law tells about the polarities of the induced EMF. So now here it is north polarity whenever the north pole of the bar magnet comes near the coil, and this is a south polarity. That means this arrow mark gives the direction of clockwise, okay? And this is known as south polarity whenever you move the bar magnet away from the coil. Have south polarity. So that is all about your Lenz law. And what is conservation of Lenz law, what we study here? That means whenever you move this near the coil, you have north polarity, and you know that north polarity, that means like pole and like pole repel each other, and unlike poles, this is south polarity, this bar magnet has got north pole, so both also attract each other. So the work done in bringing these two coils near and these two coils away, that is work done against the force of repulsion and work done against the force of attraction, is said to be converted into electrical energy. That is work done against repulsion and against attraction is nothing but a mechanical work. So whichever mechanical work we are supposed to do here is being converted to electrical energy. That is always about the Lenz law and conservation of the Lenz law. And next we are going on to motional EMF. When we study about motional EMF, it is a conductor which is having movement in a uniform magnetic field. That is where you study about the motional EMF, okay? So now, they might ask you like give the expression for induced EMF in a conductor. It is moving, which means to say that motion, it is having a motion, okay? So moving in a uniform magnetic field. So just draw the uniform magnetic field condition over here. These are like uniform magnetic field surrounding, that is the atmospheric condition which has got uniform magnetic field. And now we just place a conductor, a straight conductor here. This is the original conductor. So call it as P and Q. Okay. So it is said to be moving with certain velocity. Call it as V, call it as vector V, okay? So, and this conductor is said to have a length of L and it is covering an area of dx and its final position is somewhere over here, which I am writing in the dotted lines. So this is the final position, call it as P dash and Q dash. So this is the diagrammatic representation or the schematic representation for us to understand how exactly a conductor is moving in case of the uniform magnetic field, which is called as motional EMF. So now we have the area, that is the area as well as magnetic field. By having area and magnetic field, we know that there exists a flux. We already studied in the last session, the flux is nothing but the product of the area of the plane as well as the magnetic field which is passing through the plane, okay? So now when you consider this, you know that area A is nothing but the distance what it covers over here, call it as dx and it can be called as L into dx. Okay, so now we have this area and we know that the flux, that is change in flux, is nothing but the magnetic field into the area which is present over here. So now area means I can substitute as B into L into dx by the equation which is over here. Okay, so this will be the change in flux equation. So now we know that according to Faraday's law, we know that induced EMF is equal to change in flux with respect to time. Okay, so we have change in flux with respect to time is given as B into L into dx divided by dt. So we are just taking B into L and dx by dt is nothing but change in displacement, that is displacement by time taken is nothing but your velocity. So you can just give it as V. So Induced EMF is the product of magnetic field, the length and its velocity with which the body or an object or a conductor is moving. So this can be called as the expression for induced EMF in a conductor moving in a uniform magnetic field. So where V is the velocity with which a conductor is moving in a uniform magnetic field. So this is the expression for motional EMF. Having this expression, we are going to derive the energy consideration of motional EMF. So now we are deriving for what energy we consider in case of this motional EMF. So we know that we have got the motional EMF equation as epsilon is equal to BLV. So induced EMF is BLV. This equation we have derived from the previous slide. Okay. So after getting this equation is the expression for a conductor which is moving in a uniform magnetic field with certain velocity V and covering a distance of dx, and the length of the conductor is said to be L. This is the expression what we have got for it. So now we need to condense this expression and we need to get the energy what we consider for this motional EMF. Okay. So now we have, according to Ohm's law, we have V is equal to R into I. So you can rewrite this. V is nothing but the EMF what we are considering. So we can just retain your I here, which is equal to epsilon divided by R. So we have this equation. Substitute for this equation, we have I is equal to BLV divided by R. And we know that the force, that is the magnetic force on the conductor which is moving perpendicular to the field, is given by F is equal to ILB sine theta, which is equal to this we had studied in case of moving charges and magnetism. So we have I into L into B, and sine theta, I told you, because the magnetic field is perpendicular to the plane or the conductor whichever is present. So sine theta means sine 90, theta is 90 degree angle. So sine 90 is said to be 1. So ILB remains as it is with respect to 1. Okay. So now we have F is equal to ILB. So substitute for I, we have B into L into V divided by R and L into B, and on simplifying this we have F is equal to B square L square V divided by R. So we have this equation, that is the force, and remember this is that force which is acting against the direction of motion of a conductor. Okay, this force acts against the direction of motion of the conductor, which is dissipated as mechanical energy. It is dissipated as mechanical energy. So we need to work on a power which is acting against this force so the conductor can be moved properly. Okay, so for that we know that P is equal to work done with respect to time. So what is work done? It is force into displacement with respect to time. So now displacement with respect to time is nothing but the velocity. So you have P is equal to F into V. So what is F? F we have B square L square V divided by R. V into V is V square. So power which is used to act against the force is nothing but B square L square V square divided by R. So this is that energy what we are considering in case of motional EMF. So I hope it is clear, very clear for you regarding this equation. Okay. So now here we are studying regarding the eddy currents. What is meant by eddy currents? Due to the continuous change in the magnetic flux which is produced by the magnets for a conductor, there is an induced current over there. So due to the drastical change in magnetic flux, there is an induced current in the bulk pieces of a conductor. That is nothing but the eddy current. Okay. So suppose you consider this magnetic bar magnet which is present over here with certain pole, call it as north pole. There is a bar conductor which is suspended between the north pole as well as south pole. At that time you have got the oscillation due to continuous on and off of the magnetic field. Due to this continuous switching on switching off of the magnetic field through this conductor, there is a production of a induced current, and that induced current is nothing but the eddy currents. And this eddy currents is used to oppose the movement of an object, okay? And finally, it is helpful for the object to get back to its rest position. So this is the use of the eddy current. And the eddy current opposing the motion of a oscillating conductor is nothing but electromagnetic damping. Electromagnetic damping is said to be proportional to the area. That is, higher the area, higher is the electromagnetic damping, lesser the area, lesser is the electromagnetic damping. This electromagnetic damping is acting proportional to the area. Larger the area, larger is the electromagnetic damping, okay? So now, whenever there is low resistance, it is said to be there is increased eddy currents. So resistance is acting inversely proportional to the eddy currents which is present over there or produced, okay? So this eddy currents produces heating effect, and this heating effect is absorbed in dynamos, transformers. In order to reduce this heating effect, there is a laminating core which is used in the apparatus, and these laminating cores are insulated by each other. So some of the applications of this eddy currents are nothing but the magnetic brakes, electromagnetic damping, induction furnace, induction motor, speedometer, as well as energy meters. So these are the applications of the eddy currents. And next we are going on to the self-induction of a coil. So what is meant by self-induction? When it is self-induction, it is only one coil what we consider. That means to say that the phenomenon in which an EMF is induced due to the change in magnetic flux. Okay, so as I told you, there is a change in magnetic flux. That is, whenever you switch on and switch off the magnetic field which is being produced in the conductor, there is a existence of an induced EMF. That is the induced current which were called as eddy currents, which is used in electromagnetic damping, correct? So now the same thing is being observed here. That is, whenever there is switching on and switching off the magnetic field, there is an EMF which is produced, and this EMF induces the current, and this EMF is induced due to the change in the magnetic flux through the coil. As a result, we can see the variation in the same coil itself. The same coil is nothing but self-induction of a coil. So now we are studying about the coefficient of self-inductance, or that is nothing but, so coefficient of self-inductance can be defined as the magnetic flux is directly proportional to the current which is produced, okay? So this magnetic flux is equal to, well, removing the proportionality constant, you have got L into I, okay? And the self-inductance of the coil depends upon the area of cross-section and number of turns in the coil, as well as the core on which the lamination is done, okay? The wire is wound. It depends on that core also, okay? So these are the factors on which the self-inductance of the coil is depending. So now we have, when you just equate this equation to your Faraday's law, so induced EMF is equal to minus the flux divided by dt. We can rewrite it as minus L because it is constant, and we have di by dt. So this is the equation of the self-inductance of the coil when it is merged along with the Faraday's law. So whenever you try the numericals and all this numerical set of equations will work on this expression. So you have to remember this expression, and the inductor's SI unit is called as Henry. Henry is the SI unit of the inductor. So next we are going on to self-inductance of the solenoid. Here it is only the expression what you have to consider. So the expression for self-inductance of the solenoid is L is equal to nu naught nu r n square A into L. So this is said to be just the expression of the self-inductance of the solenoid. So nu naught is the permeability in case of vacuum. This is also permeability, and n square is, n means number of turns of the coil, and A is area of cross section, L is the length. This is how you will have to explain the terms of the solenoid, okay? So next we are going on to physical significance of self-inductance. Physical significance of self-inductance, here they ask the question, why exactly the self-inductance of a coil is said to be the inertia of a electricity. So it is known as inertia of electricity because whenever there is existence of the EMF, that EMF opposes the flow of the magnetic flux which is present in the coil. Okay, that is, whenever there is induced EMF in the coil, there exists a magnetic flux in the coil due to the current which is present over there. That magnetic flux opposes the field which is coming through the loop. Okay, that opposition is given in case of mechanics. You see the opposition through a concept called as inertia. The same opposition is seen in this electric field due to the self-inductance of the coil. That is why the self-inductance is called as inertia of electricity. So that question is also very much important. That is, the self-inductance of the coil is called as inertia of electricity, because whenever the coil which is present produces EMF, there is a current which is produced, the magnetic field is produced which opposes the magnetic flux which is upcoming in the coil. Next we are going on to the mutual inductance. Similarly, in case of the self-inductance, we have got this mutual inductance. So what is meant by mutual induction means we have got two coils. In self-induction we had just one coil, but in case of mutual induction we are having two coils, two inductance, okay, which are facing towards each other. This is called as an inductor. So here we have the primary coil as well as secondary coil, and this primary coil is said to be connected to a key and finally to a battery, and this is connected to the galvanometer G, which shows the which measures the current. So whenever there is a key present over here is being pressed, what happens to the primary coil over there? There is a passing of the current. Due to that increase in current which threads the two coils, that is primary coil as well as secondary coil, so there is a production of the current over here which feeds the secondary coil with the magnetic field. Whenever there is a production of current in the primary coil, there is a existence of magnetic field in the secondary coil, and this magnetic field in the secondary coil increases the induced current in the secondary coil, through which the EMF is also increased. So whenever there is a magnetic field increased in the secondary coil, this magnetic field opposes the growth of the current in the primary coil. That opposition is given to the primary coil. So this is like mutual induction. Okay, induction is nothing but opposing the growth of the current in it, okay, by opposing its magnetic field. Okay, so that is all about your mutual inductance. So what is meant by mutual induction? The opposition given to the growth of the conductor in a primary coil due to the magnetic field experienced by the secondary coil through the primary coil. Okay, so this is all about your mutual induction. So mutual induction is given in case of M. When we just calculate the coefficient of mutual inductance or only the mutual inductance, it is given as the flux is directly proportional to the current which is passing. Okay, so whenever there is flux, when you remove this proportionality constant, you have coefficient of mutual inductance M into I. Okay, when you apply this to the Faraday's law, we have epsilon is equal to minus d phi divided by dt. On applying epsilon is equal to minus m into di by dt. So again, coming back to the expression, this expression is also very much important in the exam point of view for your numerical. So next we are going on to the last concept, that is AC generator. So here AC generator, AC means the full form is alternating current generator. Alternating current and the direct current difference is nothing but direct current is only the current which moves in one single direction. Okay, alternating means it moves in an alternative direction, so it occupies different directions. Sometimes at certain instant of time it moves in one direction, and after certain interval of time it occupies the opposite direction, so which is very much dangerous. So direct current is safest than that of the alternating current. So here we have got the alternating current to study about the working construction of and as well as the theory of alternating current. As you can see in this diagram, we have two poles, and the components of AC generators are said to be, there are two poles that is called as field magnets, and then we have a coil in between, and that coil is wound by the copper turnings, insulated copper wire, and that middle coil is said to be the armature. And finally, we are provided with two rings, ring 1 and ring 2. And finally, there are two rings are produced with the brushes, call it as B1 as well as B2. There are two brushes. So now suppose we have a magnetic field N, North Pole, and this is the South Pole. There is a coil which is present, and that coil is provided with the rings. So this is said to be resistor, and this is also provided with one. And we have brush 1, ring 1, second brush B2, R2. These two are rings, and this is the axis of rotation. Call this as A, B, C and D ring. Okay, so this is the apparatus of this AC generator, how exactly it's moving. Actual diagram you can see over here, that means to say that this magnetic field is said to be perpendicular to this axis of rotation of the coil. Okay, so we have three components: field magnets, which is the one which produces magnetic field through the coil, and that is perpendicular to the axis of the coil. And we have a copper insulated wire which is wound on a coil, and that is said to be the armature, which rotates. And for this rotation, R1 and R2, two rings, are the supportive components, and B1 and B2 brushes are the one which passes the current through the coil. So these are the uses of these components. And finally, we are studying about the working, how exactly it works. Okay, so we know that according to Fleming's left hand rule, whenever you hold left fingers in such a way that it gives the Fleming's left hand rule, it is to say that the thumb finger indicates the direction of motion of the conductor, the forefinger indicates the direction of the magnetic field, and the central finger indicates the direction of current through it, and that is nothing but the induced current. So these three fingers gives the Fleming's left hand rule of the left hand. Okay, so having this concept, we are giving the working of the AC generator. So how exactly it works? So whenever there is production of magnetic field which is passing perpendicularly to the direction of the coil, perpendicular to the coil, what happens? The coil starts rotating with the help of rings. The coil rotates in such a way that the arm AD moves downwards and arm BC moves upwards. Okay, when that happens, this arrow mark indicates that direction of axis of rotation. So when that happens, there is a production of the current according to Fleming's left hand rule, and the production of current is said to be in the direction of CBAD direction. The arrow marks indicates the direction of current I, which then is passed to this brush, call it as B2, and then it passes through this circuit, and finally it reaches the brush B1, and again it starts rotating. It's a cyclical process, and after one half of the cycle, again your DC arm, it turns downwards, and AD arm, it comes upwards. Okay, the inverse rotation, the opposite rotation of the previous one. When that happens, again your current passes from DABC in the opposite direction, which passes through the brush B1, and finally it reaches the brush B2. Again, the second half of the cycle, the current is altered. Okay, these are the alternating movement or the motion of the current in the coil. This is how exactly the generator works. So this is the working of the generator. Coming to the theoretical part, so we know that we have got the two poles, call it as North Pole, and this is called as South Pole, and the magnetic field lines passes between North Pole and South Pole. So there is a armature which is moving over here, so it makes an angle theta with respect to the magnetic field vector B. Okay, so when the armature rotates, we have got the equation as it makes an angle. So angular velocity is present over there. We know that velocity is equal to displacement time by time taken. So at what angle it is displaced? In theta. So theta is equal to omega into t is the equation. The magnetic flux linked with the coil at certain instant of time. So Magnetic flux linked with the coil is nothing but N is number of turns of the coil and A is the area, and we have the magnetic field, and the trigonometric function which is associated will be cos theta. So we have NAB cos theta is given as omega t, cos omega t. This is said to be the magnetic flux which is linked with the coil. So whenever we introduce this concept for Faraday's law, we have epsilon is equal to minus d flux divided by dt, which can be written as minus NAB cos omega t divided by dt. So on giving this in flux condition, you have epsilon is equal to NAB is taken outside, negative of NAB because it's constant. So d cos omega t is minus sin omega t into omega. Okay, because this is due to the chain rule. Okay, next we have epsilon is equal to minus NA omega. So minus into minus, it becomes plus. NAB omega is nothing but it is called as epsilon naught and sine omega t, and this equation gives the instantaneous velocity of the generator. Okay, instantaneous velocity of the motion of this armature. Okay, so when that is the case, this equation is very much helpful in case of your numericals. And after this, we know that whenever there is a alternating current is the one which changes direction at certain interval of time, right? So this can be given by the graphical representation that if this is the axis of time and this is induced EMF, we have the sinusoidal wave given to this AC generator, which is given as 0, and here it is pi by 2, here it is pi, and we have 3 pi by 2, and we have 2 pi, and we have here 5 pi by 2, and here we have 3 pi. It goes on, continues in that way. Okay, understood? For every half of the cycle, we have change in the direction, that is change in the waves. Direction is opposite to each other. That is nothing but this AC generator. So that is all about your AC generator concept. In today's class, we have studied about the eddy currents, self-inductance of a coil, mutual inductance of a coil, and applications of this eddy currents, Lenz law, its conservation, and finally the AC generator. Let us all meet in our next class with the upcoming session of the different chapter. Until then, have a good day. Thank you.